Hello, my name is Shin. In this video, I will explain the book How to Deal with Variance, Maximizing Quality, which was published by Jujutsu Hiransia in Japan. This video aims to present a new approach to designers and analysts seeking to improve quality. The knowledge shared is beneficial not only for professionals in the sciences but also for anyone interested in understanding real-world phenomena through mathematics, regardless of whether they come from a technical or non-technical background. This new methodology is designed to be more easily understood by beginners who do not have preconceived notions, rather than experts with extensive knowledge of traditional methods. This content is for anyone curious about new ideas. Additionally, there was a suggestion to disclose the author's past career experience, which has been included in the description below. Today, I will explain an example of balance analysis using distribution functions, which was added after the publication of the book. Balance analysis is a method for finding equilibrium points where two corresponding parameters, like supply and demand curves in economics, meet. By using distribution operations, we can rigorously model this equilibrium. In traditional economics textbooks, supply and demand curves are typically illustrated as rough image curves with respect to price, focusing on the changes in these curves. However, in How to Deal with Variance, we define the demand distribution with respect to price and the supply distribution with respect to price. The equilibrium point is then determined by their cumulative distributions. This allows us to simulate the system as a computational loop embedded in the market model. This makes it possible to accurately predict the results of various economic policies, such as activating or slowing down economic activities. In How to Deal with Variance, we do not approximate the parameters with normal distributions but rather use histogram-based distributions. This allows us to precisely calculate the probabilistic results of operations between distributions. Balance analysis is one of the metrics that can be derived from such operations. Next, I will explain the full set of tools that I have made available for performing the operations defined in How to Deal with Variance and the additional features that I have added for balance analysis. In addition to the tools released at the time of the book's publication, I have since developed a tool that functions as a Python library on Windows. This library is available here. The functions available in this library are outlined in function.pdf, and the function table in the document is color-coded into 3 categories: blue, green, and red, following the steps of the operation process. Here's how it's organized. Step 0 contains functions that generate histogram-based distributions from various datasets. Step 1 consists of distribution operations and integration functions that perform calculations using the generated distributions. These are referred to as distribution operations and distribution integrals. Step 2 includes judgment indices for the results of the calculations, used to assess the final distributions. A common application in software or hardware design is using the Step 2 comparison functions, which I explain in detail in the book and other videos. These functions compare the hierarchical relationships of two distributions, such as whether one distribution is greater or less than the other. They are derived from the product of the values of the probability distribution and the cumulative distribution. In simulations, one frequently used function is the approach function, which I also explain in other videos. This function is derived from the product of the extended distributions of two probability distributions. What I will explain today is the balance function, which is used to explore the equilibrium point where two opposing curves, like supply and demand, meet. This function is derived from the cumulative distributions of the two opposing curves. To use this balance function, I have added the following 2 features, which I will now explain. One of the new features added in order to include the balance function is a modification to the distribution class. Previously, the operations targeted probability distributions, but with new feature 1, I have expanded the distribution class to include physical quantities where the total area is not equal to 1. This allows the exploration of equilibrium points as integrals of distributions. Until now, the distributions used in How to Handle Variability were kernel distributions generated as probability distributions, similar in shape to histograms created from data. These distributions were adjusted so that their area equals 1. With new feature 1, when generating a distribution from data, you can specify the value of the area using the volume argument. In some functions, the distribution will now be processed with the area equal to the given volume. Additionally, when generating distributions by directly reading histograms, the sum of the histogram values is treated as the volume, allowing for the generation of similar distributions. For example, when dealing with dual distributions, like the demand distribution and supply distribution, the balance function can read these sets. It then generates cumulative distributions in the negative and positive directions, searching for the intersection point. If the provided distributions are for demand and supply, the parameter value at the intersection corresponds to the equilibrium price, and the height of the intersection point represents the sales volume. It should be noted that the demand-supply curve used in economics has price on the vertical axis and sales on the horizontal axis, but the vertical and horizontal axes are reversed because it is treated as a distribution. Additional feature: operations on distributions with correlation coefficients of 1 and -1. When performing operations on distributions x and y, our previous method handled either the case where x and y are statistically independent or cases where their correlation coefficient lies somewhere between -1 and 1. In the case of statistical independence, for example, when calculating the distribution of the product z equals x multiplying y, the value z1 corresponds to a curve shown as a red dashed line in the xy space where the product xy equals z1. By dividing this curve into small segments and summing the product of the probability densities of the corresponding x and y values, we can compute the probability for z1. Repeating this for evenly spaced z1 values across the distribution range gives the full distribution of z. This computation is performed within the green rectangular region that represents the range of x and y distributions. If we narrow this region to a diamond-shaped area centered on the diagonal of the rectangle, we can simulate intermediate correlation levels. The newly added feature enables computation for the extreme cases where the correlation coefficient is exactly 1 or -1. In these cases, the operations are not performed over a region but strictly along the diagonal of the rectangle, either from bottom left to top right correlation equals 1 or from top left to bottom right correlation equals -1. If distributions x and y have similar shapes, this diagonal becomes a straight line. If their shapes differ, the curve adjusts accordingly. This means x and y are paired 1 to 1, and their weights are non-linearly adjusted based on the shapes of their distributions. With this new feature, for a correlation of +1, an upward-sloping diagonal curve is calculated. For a correlation of -1, a downward-sloping diagonal curve is used. This allows us to compute the resulting distribution from these perfectly correlated cases. In the following sections, I will explain how we use this new feature along with the balance function to construct models and run simulations using distributions of income, demand, and corporate product supply. This is the model used to simulate demand-supply balance. The calculation script used is script12.py, which can be found in the GitHub repository skoike/bungpoo3. I will also explain the functions defined within that script. On the left side is the flow to calculate the demand distribution. On the right side is the flow to calculate the supply distribution. At the bottom center, a balance analysis is performed using the cumulative demand distribution, accumulated from the negative side. The cumulative supply distribution, accumulated from the positive side. Using these, the equilibrium price and sales volume are determined. 20% of the calculated sales is allocated to capital investment depreciation, which is reflected in the cost. In the next section, I will explain how the demand distribution on the left side is derived. Explanation of the flow on the left side. Calculating the demand distribution first, the distribution of disposable income is calculated based on the distribution of national income and the distribution of the burden rate, which includes taxes and social security. Each of these distributions is shaped as shown in the diagram. The burden rate represents the ratio of taxes and social security to national income. Since there is a 1-to-1 correspondence between income and burden rate, the burden rate distribution is generated by combining the burden rate per income level, the proportion of each income level. The burden rate data per income level is based on the research of Professor Shimazawa of Kanto Gakuin University. The disposable income distribution is derived from the product of the national income distribution, the distribution of 1 minus burden rate. This product is treated as the disposable income distribution. Since the burden rate has a 1-to-1 correspondence with income, its distribution is defined such that the probability values correspond to income proportions. Thus, the two distributions are negatively correlated, correlation coefficient of -1, and the product operation is performed accordingly. This negative correlation computation is a new feature referred to as new feature 2 added to the distribution engine. In this analysis, we begin with the burden rate data from 1994 to observe its impact. Later, we will compare it with the 2022 data. At the bottom, the functions are shown. The first line computes the distribution of 1 minus burden rate, stored as Kaziyabun ratio. The second line calculates the product of this distribution with the income distribution to get the disposable income distribution. The last argument -1 specifies that the distributions are negatively correlated. If not specified, the default calculation assumes independent distributions. Next step. From disposable income distribution and willingness to pay distribution to demand distribution. The demand distribution is calculated by combining the disposable income distribution and the willingness to pay distribution. The chart shows the shapes of each distribution. The willingness to pay distribution top right reflects how many people based on their disposable income are willing to buy a product at a given price. For example, if the price is low relative to income, more people will buy. If the price is high, fewer people will buy. This distribution is based on an assumed product priced around 100,000 yen, with an estimated market size of 60 million yen. While most other distributions used in this model are probability distributions area equals 1, this willingness to pay distribution is defined such that its area equals the market size. This is implemented using new feature 1, which allows defining such scaled distributions. The demand distribution is the result of multiplying the disposable income distribution, the willingness to pay distribution. The two distributions are treated as independent, since willingness to pay is assumed not to depend on individual income level. The code uses the function bunp_gene to generate the willingness to pay distribution will-pay ratio, and then multiplies it by the disposable income distribution after tax to obtain the demand distribution demand. The area of the willingness to pay distribution is set to 60 million yen to match the market size. Next, on the right side, the flow for determining the supply distribution is described. Supply distribution calculation flow. First, the cost distribution is derived from two components: the distribution of material costs, the distribution of capital investment equipment costs. These distributions look like the ones shown in the chart. However, over time, the equipment investment is depreciated annually, which causes the cost to decrease year by year as sales increase. As shown in the formula, the 20% of the capital investment is depreciated each year based on annual sales. The remaining value of the equipment is divided by the number of units produced, and this result is added to the material cost to calculate the total cost. The simulation assumes a 3-year timeframe. In the first year, the cost distribution includes both the material cost and initial equipment cost. From the second year onward, as the equipment cost is depreciated, the cost becomes primarily composed of material cost only. Calculating the supply distribution next. The supply distribution is derived from the cost distribution and the willingness to sell distribution. These are the corresponding distributions. The willingness to sell distribution top right shows how much production risk a company is willing to take depending on how much higher the selling price is compared to the cost. If the price is significantly higher than the cost, companies are more willing to prepare for large-scale production. If the expected price is not much higher than the cost, they will prepare for smaller-scale production to mitigate risk. Based on this logic, we modeled this distribution using our custom function 1, where the area under the curve corresponds to the potential market size or maximum sales amount. Using the function bunp_gene, we generate the willingness to sell distribution, and by multiplying it with the cost distribution, we calculate the supply distribution. The area of the willingness to sell distribution represents the maximum sales value, which is set to 60 million yen. Next, we will simulate how sales change when products are sold at prices aligned with the varying cost distribution over time. Final step, balance analysis. Finally, a balance analysis is performed using the demand distribution and the supply distribution. From this, we calculate the equilibrium price and the sales amount. 20% of the resulting sales amount is allocated to depreciation of capital investment, which leads to a reduction in product cost in the following year. The result of the balance analysis using the demand and supply distributions is shown here. The cumulative distribution of demand accumulated in the negative direction and the cumulative distribution of supply accumulated in the positive direction are plotted along the price axis. The point where these two curves intersect is the equilibrium price, and the height of the intersection point represents the sales amount. The sales amount and the equilibrium price is annotated on the graph. 3-year simulation based on national burden ratios. The upper chart shows a 3-year simulation based on the 1994 national burden ratio distribution. The lower chart shows the same simulation using the 2022 distribution. All conditions except the burden ratio are kept constant. Simulation logic: in the first year, cost and price are determined based on the planned production volume, and sales are calculated from the demand. From the second year onward, cost depreciation is reflected based on the previous year's sales amount, which affects the supply distribution. If sales are strong, the supply distribution shifts leftward, reducing costs and increasing sales. If sales are weak, the supply shifts rightward, increasing costs and decreasing sales. In both scenarios, the first-year equilibrium prices are similar, and the sales difference is minor. However, from the second year, the gap widens. Under the 1994 burden ratio, costs drop significantly, shifting the equilibrium point upward, leading to increased sales. Under the 2022 burden ratio, sales decline, production volume falls, costs rise, and prices increase. By the third year, sales plummet and costs spike, withdrawal becomes inevitable. Corporate tax impact. The graph on the far right shows how corporate tax payments change with each scenario. As the tax rate increases, the burden ratio rises, which reduces company sales and thus lowers tax revenue. This suggests that to improve fiscal health, tax reduction may be more effective than increasing taxes. Conclusion: by defining demand and supply as distributions, I was able to incorporate the supply-demand balance into a time series simulation and forecast economic activity. This approach was made possible by representing changes in market size and production volume as variations in the shapes of distributions. It is believed that this method can be applied not only to product demand-supply balances but also to the design of balances in various social and physical phenomena, enabling high-precision modeling. Through this economic activity simulation, it became clear that changes in the national burden ratio have a significant impact on market conditions. Under the burden ratio from 30 years ago, companies could grow significantly, whereas under the current burden ratio, sustainable operation has become difficult. I hope that this new simulation method will be utilized by the government and the Bank of Japan and reflected in policies aimed at revitalizing the economy. This concludes the video. Below, you will find the links to tools for applying this method, the book purchase site. The tools I put on GitHub are free for learning purposes, but must be the same version of Python as described in env.txt. Install the same version of Python in a virtual environment such as Anaconda. If you need further assistance or if you are going to make commercial use of the software, please contact me at the address written in the README license. Thank you very much for watching.